Hey guys, this is a walkthrough of the precision challenge from CSAW. So it's a very basic exploitation challenge, but with a little weirdness to it. So I think that's a cool way to have an introduction to GDB and binary exploitation and some small little things that will slow you down, and if you know them, that will make you very fast with it. So the binary, you can download it here, and there's a netcat address you can connect to, so we can also try this out really quick. So if you connect to it, it tells you a buffer address, so it looks clearly like an address, and buffer, the name already tells you, okay, it has something to do with the buffer in memory. So this is probably very important for the exploit. Probably it uses ASLR, so it randomizes the addresses, and it's nice that it gives you the buffer, so that you can know the address where you, for example, have to jump to. So this is already very clear. So if you download it, I have already downloaded it, then you should check what kind of file you got. So it's a 32-bit Linux binary. It's not stripped. This means that you will find names of functions and stuff into it, which makes it very easy and nice. Also, a very good idea is always to do strings -a on the binary to get all the strings in there. And there's nothing particularly interesting in it, just that we see here the strings, like this buff, for example, here. Or we also should maybe, like, just as a test, show you here, got a. So the next step is just quick my setup. So I have a VM here running with a Linux 32-bit, and I have SSH into these one of these three windows into there. And here's my my Linux machine, my Mac. So first thing is, if you open this in GDB, as you may have tried this before, and for example, let's just set a breakpoint in main and let's start this program. You will see it has this, it stopped at the breakpoint, and now you would like go with check the registers or disassemble main, and this is very tedious to figure out where you actually are, and then you forgot, oh damn, where was I? Oh, EIP here, and then you have to compare like where you were. This makes if you don't know what you're looking for, makes you very slow. That's why so many people like OllyGDB and WinDB debugger, like those user interface tools. But there's a neat way to make this a lot better quickly. there are other tools that may be worth investing into, like PEDA, or I don't know how it's written, like it's this exploitation, Python exploitation assistance for GDB. I have never tried this myself. So, but what I usually do, I get a GDB in it. This one is nice. I don't know. I don't have a particular one that I like or anything, but I just use this one from a guy that builds it for specifically Mac. But I will use it on Linux. It will just make things look nicer. So you can just like get the GDB in it here as raw, and then you can just download it, which I already did, and then you can load this binary. And you already see that like GDB -x, you specify the GDB init file. It also has some color, and if I break on main and I start again, you will notice that it will display me all the registers. Actually, it displays me all of them, but because the background and the foreground color is black and I didn't change that, it's intended for a white terminal. Anyway, and down here you see the current code where you are, and then when you start stepping through, the code moves on, and you always see the last changed registers in red. So this is already a very visual way of seeing what you're debugging, and this is already great. Okay, so next step. Let's have a closer look at the binary. I threw it into Hopper and IDA, but I will focus on IDA right now. So this is the main function you will get into, and the first thing I usually do is like a quick scan. I just like try to understand what those blocks mean, and especially like with the syscalls like printf and scanf, because that will tell you already roughly what will happen. So if you look quickly, okay, it loads here weirdly, std out set vbuff. I don't know what stvbuff means, so I ignore it for now, but it prints buff, the address. And then it does scanf, so this is when it waits for input, and then it does a compare or anything, like there are branches, check something, and if it was wrong, it will print nope and write that. That's puts, or printf is writing it, and then it will exit. So it will just exit the program. But if this is successful, then it will go in here, will do a printf. This is the got. Oh no, wait, no, that is wrong. But anyway, it shows you what you input into the binary. Like it would printf this here, and instead of exit, it will then return. So let's assume you would overwrite the stack with a lot of garbage, and you are waiting for the return to come, so you can get codecs to jump to your overwritten EIP. In this case, it wouldn't work because it would exit. But in the true case, if you have follow the tree down here, then you would have the return, and the return would then jump to your overwritten value. So this is our goal here. So now we have a rough idea. So the first thing probably would be nice. Let's just throw in there like a bunch of characters, and let's see if this thing seg faults. So let's make a lot, and it says nope. Damn, it exited. Okay, so it clearly got to this exit. So now let's take let's have a closer look what's happening here. So here's a branch. Those weird assembler instructions, I didn't know them either, because they are, as it turns out, floating point stuff, and I've never worked with that really. But you can quickly Google this and you will figure out what they are roughly doing. So up here, it's like floating load. So it's loading a floating point value on the so there's, as far as I understand it, there's like a separate stack for in the CPU for the floating point calculations. So it loads a floating point value on the stack, and then it stores the latest floating point value on the stack, the topmost here on the stack. So it reads a floating point value and stores it somewhere on the stack. Then comes our the printf and its scanf. So obviously we'll probably have the overflow after the scanf, because we will probably read too many characters. And then what it will do, it will load the same address where it previously wrote the floating point value. Then it will load the original value, and then it will do a floating point compare, and that from this floating point stack. It doesn't matter. So basically it's loading a floating point value, writing it somewhere on the stack. We overwrite the stack, and then it's loading this stack value again and the original one, and now it compares them and checks if they are still the same. So basically this is kind of like a stack canary. So let me draw this. Let's think about this, how this looks. So you have, you know, all your data like that you scanf, and then in the middle you have some floating point value here, like 0 point something, and then you have back here EIP, and now you want to overwrite this. So you trash this floating point value, and now you overwrite EIP with, you know, your dead beef. That's where you want to jump to. But now comes the check, and it will read those A's, and it will realize, oh, those A's are not like the original value that we wanted to have there, and it will exit. So what you have to do is we have to smash the stack and overflow everything, but in our overflow we have to include this float value, okay? And then back there we overwrite EIP, and now it will be successful, and this will be equal, and then we will jump to dead beef. So that's the theory, and we will have a look at this now. Okay, so let's have a look in GDB how this looks like. So first of all, we disassemble main, and let's make this a little bit bigger, and we set breakpoints in important parts. So I mean, this is basically the same that is happening here, where it's loading those floating point values and then comes to compare. So let's load these values and break here. So we restart the binary, we continue. Now we have our input, so this input is very short, so now we would see what those values are. So we can do info float, and we will see that the both floating, so this is this stack I was talking about, like that's in the CPU for floating point calculations, as far as I understand. I'm sorry if I say something wrong. So the first float loaded the first value, and the next float loaded the next one, and now it makes a compare on the stack here between those two values, and it checks if they are basically the same. So also we wanna like check where those value actually came from. So if we look at the disassembly here, so this one value came from here. So I know that it's so usually like with x, one wide, so examine one value which is a wide, which is wide, so it's 4 byte, and we want to interpret this as hex and then the address. Fail. Wait. Okay, that was embarrassing. Anyway, it was an X here. I don't know what happened here. It's obviously so X for hex. I confused myself by saying it out loud. So 2 bytes long. So this is the float value, and it that is loaded from this address here, and it has to be the same as, let's do basically the same thing, but this time from ESP plus 18. Oh no, right, I'm wrong. Here, ESP plus hex 98. So this one is the same. Okay, let's start again, and let's throw in like a lot of values to smash the stack, and then let's look into the floats. And now this is clearly garbage that is here. If you want to know why this is not for one, you have to look into how floating point values are handled, and it's horrible, and nobody wants to learn how and understand how it works. So, and now we look into those 2 memory regions. So this is the original one, and now the one on the stack, and that's for one. So let's restart again, and now I make a breakpoint after the original load, so I continue there. If we compare it at the start, you see that on the stack is normal. So what I also like to do is like look at the whole stack. So examine 46 values from the stack, and we can look here. So at C78, so here and here, this is basically the float. And if we continue now and we enter like this super long string here, and we do now the same thing, you see how we have overwritten everything on the stack, including at 7.8 the value here. And obviously further back here somewhere, like after this one here, one of these other values, so like one of these values here, I don't know which one, will then be the instruction pointer that we would have to have overwritten. And now when we continue, now comes the comparison. It will put now the nope and then exit. So now we can start building our exploit. So let me open a file for this, and we call this precision.py, and now we can start writing Python code here. So first thing is we want to get the exact offset of where the float has to be. You can use create pattern from Metasploit, but I don't have Metasploit on here, so I just do it by hand. And I do this by I start again, continue, and continue, and then I like just put in a bunch of A's here. Oh wait. So I put in like 100 A's plus, and now I just create my own pattern. And now I put this in here. Now I have the breakpoint. Now I look at the value on the stack. That should be that should be our float, which it's not. So it's a 49, and you can look here with Python. You can put in the 49, and that is an I. So here, this here, the I and the J, those is the floating point values. So I can copy this one here, and we can start building our exploit string. So I call this buffer. Start with an empty string, and then we have basically 100 A's plus until we reach the what's it called? Until we reach the float values. So so this is 28 characters long, so we can make 128 A's, and that's cool. So then we have to put in the floating point, and here's a neat little trick. So we use Python struct to convert numbers into a binary string, and I create a small lambda, anonymous lambda function here, or however it's called. By doing it like this, you just can remember this because it's super cool. Lambda x struct dot pack I, that is like, it's an integer, so it's 4 byte, and then here, so x is, so this is equivalent to def x return struct pack I. So this is this x, and this x back here is the parameter, and this is the return value, and x is the function name. Okay, so it's just a fancy one-liner to do this. So the values that we actually want are not break, damn it. Okay, so those are the two values, and now you can do this. You can, so this is a number in Python, right? It's just the hex representation of the number, so this would be this integer, and this is the other one, and we can just do now this trick, and this will convert automatically into the string. So if I copy this one, for example, you will see it will create a string encode as hex, for example. So you will see it's the 51, the 15, the 50, and the 40 here. Okay, cool. So now I think we should have the float, and now we need to fill up again, and we now need the how much we have to fill it up until we reach the instruction pointer. So I do the same thing again. I make a pattern that's easy recognizable. And yeah, I hope that's enough. I don't remember. So, and then at the end I just print this exploit buffer. And so now I have to think about how I do this. I think I will, so Python precision will now print this string here. I will print this in, I will pipe this into a file, and then I will I need the address, and then I will SCP this file onto the server. Okay, so it copied the file up there, and now I can do run preg on this file. There are better ways how to do this. LLK will probably set something up cool that you can like directly on your file system, like maybe SSHFS or something, whatever. So now it should be in there, so we continue. So now comes the compare. Let's have a look at the float. The floats are correct. Maybe we didn't override it, so let's look at the stack if we actually did this. And we can see here all our A's. Here is the float, and then back there is the pattern, the 0, 1, 2, 3. Another thing that I wanna use this moment right now is how easily you can recognize strings and characters in memory. So if you look at this, you can immediately tell what certain values are. So as you see, the stack usually grows from high addresses lower. So all these BFFF addresses here, those values are stack addresses, whatever they are used for. Okay, it doesn't matter. If you look in the disassembly of main, you will see that it starts as 080. So all these and those are usually the same. It depends if it's like ASLR or anything, but if you open them in GDB and if you open it like in IDA, you will notice they are all at 080. So this is like the standard where the binary is loaded. So all those 080 values are addresses that point to the binary in some way. Okay. And obviously the ones with many zeros are usually like single values, like this a counter or a length or something like that, so like 20 hex or something. The ones with B7, I think they are usually they are from like libc. So for example, the printf function or the system function, they are like in libc and they are loaded at B7. I don't info very no. Oh, that was probably stupid. Info functions. Yeah. So you see here, like for example, malloc, realloc, they are all loaded at B7. So this is also a very common place where libc is loaded. So just by looking at the values on the stack, you immediately can tell what those things are, and then you also can see that this looks like strings, like in the certain range. You can look here, if you look at the ASCII table, so the characters basically start here at hex 33. Those are that's where the printable characters started, and that's basically the from 33 or 32. Oh wait, this is octal. No, that's this one. Okay, here hex. From 20, hex 20, it just continuously goes up, like the capital letters, all the way up, and higher than that, it's all printable characters. So everything that's between 30 and like 80 or something, or 70 something, are characters. So immediately you can tell, okay, this is a printable character. And then you can do like something like print 6 strings from the stack. Okay, we need a bit more. And then you will see here A repeats 128 times, and 5, 6, 7, 8, 9 is the other string here. So just to give you like a feeling for how to interpret hex values, and what they can even tell you without actually knowing what is behind them. Anyway, so this worked. Now let's continue and see if we get a segmentation fault, and we do. So we successfully have overwritten the instruction pointer with 3333, which is pretty cool. You don't have to actually convert this to like which we did with the previous character. 33 is just the value 3, because numbers start from 30 up to 39, and you basically can just like remove the subtract 30 or remove the 3 here, and you know which number it is. So that's number 3. That means that we have 16 characters of padding between the floating point number and our EIP. So we can just put here some 16 Bs. Oh, 12. No, 16 including the EIP. So like that. And basically the next value here is the stack pointer. Or wait, is the instruction pointer where we want to jump to, okay? This is our way how to control the instruction pointer. Now we wanna know where we jump to. Where we wanna jump to. So let's see. If we continue again and again, and we look at this output of the buffer, if you just paid attention to what you can recognize those values from, you immediately know, huh, this looks like a stack address. And indeed, this is a stack address. So if we look here at the ESP and we look at where BF8 is, it's a bit higher than this. So we go a bit back, a bit more. So here it is. And as you can see, the output that was given here from the like if you make netcat to the server and you look at the address here, this address that is given you here points at the start of your buffer. See, this is where our A's start. So we can put there our shell, so we can use this address to know where our shellcode will be. So this is the idea to place their shellcode now. So this is what we are going to do. We take some shellcode. What I usually do is I go on Shellstorm because there's a collection of shellcode that you can use. Especially the Metasploit generated shellcodes are often extremely long, and often, especially those Linux kind of stuff, those here are perfect. So we go to Linux 32-bit and we select one, and I just selected a very short one. Let's see if I can find it here real quick again. So there are many. I think it was this one here. 32, 23 bytes. No, it's 21 bytes. Yeah, you can see there are a lot of and to choose from. Okay, so here's a simple 21 bytes one. Okay, so this is the shellcode. Again, do you recognize what this is? It's between 20 and like 70. So this clearly strings, and if you wanna, know what this is, you can just go in Python. Let's put these together. Decode hex, and it's bin sh. It's just because the number representation is the other way around. So that's just bin sh. It will push this on the stack, and then it will invoke interrupt 80, which is syscall. So it will just call execve with bin sh. And it will call execve with first parameter the string, the second two parameters the 0. So if you look here, x or ecx will set ecx to 0, and whatever this mul does, I have no idea. This value is then pushed on the stack. I don't know exactly why, but anyway, push this value on the stack. The next one is the string, and then it loads the value of the execve. So every syscall has a number, and the syscall execve apparently has the value b. So that's like 11 something. So the syscall number 11 is execve, and this has to be loaded in EAX. So we just take this shellcode now. I will copy this one here, and we can put it in our code. Shellcode is equal to this here. So here's a cool trick you can do in Sublime. You mark, you can highlight a certain character, and with Command D or Control D, you can highlight all of them. You have multiple cursors now, and then with Shift Command press right, you can highlight all the way to the end and remove that one. And then, you know, you can. Cool. I hope I didn't destroy anything. No, I didn't. Okay, cool. It ends with 80. So now we have this string here. And we can. So that's the shellcode. So what we do instead of the A's now. Oops, buff empty string. So instead of the A's now, we will add the. We will just, you know, it's always good to have some form of knob slide. Then we add the shellcode, and then we need to fill the buffer with A's again. I don't care, whatever. With 100, it has to be 128. The padding has to be on 128 bytes. So we take 128 byte and remove the length of how long our buffer was before. So that should give us the correct padding. And yeah, and we have to set EIP, and we do this because we test this in GDB right now. So what did it give us? The buffer that is constant here in GDB. So this is where the instruction pointer is. Okay, and now we print this again, and it should work, right? So we send this over there. We so if you press R now, it will actually, because you did this before, it will basically do the same. It pipes the uses the file as standard input for this process. So we do continue, and we would expect that this just works, but program exited with code 47. So what the hell happened here? So let's do this again. We continue, and let's have a look at the stack. And now you think, wait, what? Where's our the stuff that we put there, like our shellcode and those A's, and they are gone. Wait, am I in the, wait, no. So you see, you realize that there should be a lot of A's because the shellcode is like only 21 bytes long plus the 16 here, so there should be at least like 70, 80 A's or something, but where are they? They are not there anymore. So now we have to debug, and this is where I got stuck a little bit earlier. So clearly the knob slide is here, so here are the 90s, but then this also looks like our shellcode. You see here E1 F7 C9, E1 F7 C9, so that's fine. But then at some point it stops, so we can follow it. And so it seems like here's a null byte. So B7, you know, you remember B7 is always like a libc address. So this seems like it got a little bit here overwritten, but stopped here with a null byte. So let's see what happened there. And if we look over here, we see that at the end there's like this E3B0, E3B0, and then comes a 0B. And then it just stops and it's missing the rest. I don't know why this happens. I think this has something to do with this vbuffer set, the steady out. I have no idea. If you look into the ASCII table, the B is a special character. It's a vertical tab, so I figured that it's just a special ASCII character that for whatever reason is destroys our shellcode here, and we have to get rid of it. So here comes the next cool trick, how to fix the shellcode. So what we're gonna do is we take this shellcode here with Python. So this is a byte string, right? So this are escape sequences, like 4-1 is an A. So, and now we want to encode this into just a hex string, you know, just the hex values like 31C9, and we can take this and go to the online disassembler. So this is how I do it. There are probably better ways. and in the end we can see here the B0 0B is a move AL to 0, moves the value B in AL. So I thought, wait, I had to get rid of the 0B, and apparently this hex value corresponds to the value in the instructions. So what you can do is you can just move, you know, a high value like a valid character, even 3B, into AL, and then you just subtract from AL the base that you added to it, which is 30. So now we have a B03B instead. You can see this updating here a second, and now we just have to subtract it. So in Hopper you can with Alt A you can assemble, and then down here you see the how the instructions encoded. So I guess if you're on Linux and Windows, you have to find another way. You can do it with Oli GDB if you're on Windows, and on Linux, I don't know, we have to figure out a good way how to do this. So, and then we just subtract this value again, and that's equivalent, right? That's the same thing. So we can copy this. Now it's a bit screwed up. We have to make this all in one line again. So shell code is now this string, and like before we did, we encoded this as hex, so now we decode this hex and get back our binary string, right? So we can, this is our new shellcode. So we save this, we execute it, write it to the file, and copy it to this to the virtual machine. Continue. So let's have a look at the stack. That looks way better. See the 9990, and now it didn't stop. It has the full code and also then the ace again. So I would say we disassemble main and we break before the return, and we continue. So we are there. Now comes the return. So let's have a look on top of this on the stack again. So the current value on the stack is this address here, and if we look what's at this address, we see that's where our knob slide is. So we can now single step. Let's ignore this arrow. That's because the base pointer is also screwed up, and GDB tries to get this information for us. Anyway, so now we are here in this knob slide, and now we like execute knob, no operation. So, and then we slowly slide into our shell code, and there it is. ECX sets ECX to 0, whatever this instruction does, whatever, pushes ECX on the stack, it pushes those two strings on the stack, it does some weird other stuff. Now comes the 3B, we subtract from it again, and now we have the B in EAX, and now we can trigger the interrupt and executing the program bin dash. Awesome. So this worked. So now we have to just make this exploit work against the server, and we need to supply the buffer. So how we do this is instead of putting it there like this, I figured for this particular task I don't import socket and stuff, so we just do it by hand. So what you can do is you have raw input, like this is just reading input from standard in Python, so you can it's waiting for a string, and then the string will be converted into an integer, and we will pass it in there as hex. So yeah, that's what we do. And when we now execute this Python precision, it will wait for input, and for example I want to oh, let's make, yeah, 4, and then it will put it in this exploit string and send it out. So let's make a test. We can do netcat listen on on a port, and we execute the precision binary. So let's see how this works. On the same time, we can look here with ps3 minus p. We can see here that this is netcat. Okay, here's netcat started, and now we call Python precision and pipe it into netcat. I don't remember. Five, 6, 2, 4. So PS3 has here netcat running. Pipe this in there. We got a connection. Our Python program is waiting. So instead of netcat running, is now the precision running. So it handed. So this code here handed now the execution to the precision thing. So everything that we sent in now will be sent to the Python string. What am I talking? Everything we put in there into netcat now is executed, is handed to the precision binary, to this process. So this process is running now and it's waiting for our input. Our Python program has not sent anything yet, because the Python program itself is waiting waiting on this raw input for our value. So we put in this buffer here, and now it broke, which is sad. Wait. Does this work? Okay, I probably know the issue. Python string sends it, and then obviously it ends because there's no input. Now comes a cool trick I've learned. So first we want to execute the Python script, right? We want to send this exploit string to the server, and then we want to keep it open so that we can write something. So if you just type in cat and you type something in, this will be the output again. So whatever I put in there will echo back basically. So for example, if I do echo ISD and after that I do cat, I get echo ISD, and now I can put in stuff. For example, let's do this into a file like this. First the echo ISD got executed, and then I write something in there, and then I stop, and if we look into test, you will see first got ASD and then whatever I typed in there. So basically we do the same thing, just remotely. We execute Python precision. This gets executed. Once this is done, it will open cat, and this whole thing will be like put in parentheses, and then we open the we connect to the binary over here like that. So it got connected. Now the Python precision program is waiting for our input. We can check the PS3 again. Precision is now executed and it's waiting for our input. The Python script is waiting for our input. We give it the address for the raw input. It sends out this string, or it prints the string and it's sent there. It got received. Now we check the PS3 and you see that the previous precision binary got now replaced with bin_sh because of the execve. So this process got replaced with the shell, and now this is now precision is done. This program is not executing anymore. Now we are in cat. Whatever I put in here now will be sent through netcat to this sh process. So if I type id, I am now on this Linux machine here. So now we do the same thing with the remote server of CSAW. Instead of going there, we use this IP. So now we have this randomized buffer. Our Python script is waiting for our input of the address. It sends this, and now it should work. ID CTF cat flag. There it is. Uname -a. Let's see what other people are doing there. Yeah. Anyway, so and here's the flag.